Welcome back, my structural analysis friends. In our last video, we started looking at energy derivations using basic physics principles and how we could relate internal work energy to external work energy. In this video, we're going to actually start putting those to work in determining deflections, and we'll start our discussion today with trusses. And so we'll walk through the basics of calculating internal work energy for trusses and show how this method can be put to use. So without further ado, let's get started. So as we start to try to apply the method of virtual work for trusses, we're going to set up our derivation by starting first with a member definition and kind of get an understanding of what's going on with a single member, and then we'll turn that into a behavior of a system of members. And so this will be our first use of using energy methods to determine a system's behavior. All right, so here's where we'll get ourselves going here. So first thing we need to do is remember what are the basic properties of trusses. The first one is that all members are axially loaded, that all members are pinned at the ends, and that all members are straight. Okay, all of that means that there's no moment anywhere in an axial member. It's just either a member that's in tension, which is what I have drawn here, or in compression, and so on. Now, we can use our methods for compression-based trusses as well. It's just that we're going to neglect the effects of buckling in this and any sort of increase in displacement. Now, back in statics, we learned how to do truss analysis by method of sections, method of joints, and all that still basically applies, but now we're talking about deformable bodies, so we're going to relax the restriction that the member can't change length, and today we're going to start taking that into account. So what I have here is I have an axial tension member of length L, okay, with a load acting on that member, a value of P. Okay, the member itself has a cross-sectional area of A, and it is made out of some material with a Young's modulus that we're just going to call as E. Okay, we know from our basic mechanics principles that if I pull on this member and it's a deformable body, it will grow in length. Okay, so the growth in this member we're going to call as this little delta here. Okay, now things that we can calculate from mechanics. We can calculate the stress in the member. That's just simply P over A, which is my sigma, and the strain in the member, which is basically the change in length over the original length. Okay, we know that Hooke's law is sigma equals E times epsilon, and so if I plug in these two equations into Hooke's law, I get something that looks like this. P over A is equal to E delta over L, and we can rearrange and solve for our axial deformation delta as being PL over AE. And this is pretty cool because we now have a deflection and a load and then a material constant. This is the K, this is the stiffness. This AE over L term is the stiffness of the member. Okay, L over AE ends up being the flexibility. It's something a little different, but it's still, there's a linear relationship that exists because we're assuming that displacements are small, the length doesn't change much, the area doesn't change, and the E doesn't change. Now again, we've kind of neglected any sort of Poisson effect, that if I pulled on this member in our tensile test experiments, we saw that there was a necking that occurred and the area changed. We're going to assume that the area doesn't change much, that it's constant there. Okay, so that's what we're going to do. Now, the way that we start to examine a truss is as follows. Okay, we're going to be creating two systems. One is the real system, one is the virtual system. And so the real system is basically, I have my structure. This is just a simple 5-member truss here that has a horizontal point load P1 and a vertical load P2. And under these loads, we would expect that this truss would deform into what you see as the dashed line portion, right? The P1 kind of forces the node over, and P2 forces it down. A and C can't really move. I guess C could move a little bit horizontally. B can move down and over a little bit. A doesn't go anywhere because of the boundary conditions. All right, and so we're going to look at just taking one member out of this system. We're going to call that as member J. Okay, and so the deflection in this member then is going to be PL over AE. It's that same formula we derived here, and his change in length is going to be based on the load that shows up in him. Okay, and so that's our real system. And so we'll go through and we'll analyze this truss using our method of sections, method of joints to find all the forces in the member, and we'll be able to get this P value for every member in the truss. Every member is different. Okay, the virtual system is a system that I'm going to set up such that I put a unit load, 1 kip, on the structure. So in this particular example, I'm after trying to find the deflection in the vertical direction at B. Okay, so the way that we set up our virtual system is we apply a 1 kip load at the point of interest. So if I want a vertical deflection at B, I put a vertical load at B of 1 kip. If I wanted a horizontal at D, I put a horizontal 1 kip. Okay, and so this virtual system changes depending on what it is that you're trying to find. And what you'll do is you'll take this 1 kip load and we'll solve for what the virtual forces in the member are. Okay, so my member J, if we have it here, is will be it will have some force that's a function of this 1 kip load. Now what this allows us to do is it allows us then to be able to scale behaviors accordingly. All right, so the idea is that I'm going to be setting a 1 kip load in the direction I'm interested in at the location that I'm interested in. And that's the only load that goes on this system, no other loads. And then you basically reanalyze the structure. So you can see for trusses, it means you got to solve the truss twice, which is kind of a pain. Now, if we go back to our virtual work principles, and we're a little fuzzy here. Let's see if we can focus this a little better. All right, I think that's a little better. Kind of the focus is acting kind of weird. Sorry about that. Okay, so we've talked about the trusses. Okay, so my work energy calculations then are that if we look at the virtual external work that's done by the 1 kip load, then we know that this point is going to move down vertically some amount delta, which happens to be the delta that I'm looking at. So the virtual external work on this system then is 1 kip times that delta amount. Okay, the virtual internal work energy of our member J, of this guy then, for each member is simply the force in that member multiplied by the elongation of that member. Okay, so that's FV times delta. And you do that for each member in the system, so there will be a sum of this. Okay, so then the total virtual internal work is simply the summation of all of the work pieces of all of the individual members on this. So I'm going to do a summation of all of the FV deltas for every member in this system. And we know that the delta that we were calculating on this was PL over AE by definition. So then that's the true delta. Okay, so then if that's a true delta, then this becomes the real force in the member. This P came from this picture, whereas the virtual FV came from this one. Okay, and so you'll see that, and then you just simply sum this quantity, FV times PL over AE, for every member in the system. Now, in some textbooks, you'll see this written as little n and big N. I think our Casamali text doesn't use this, but things like Hibbler and some of the other methods will use a different nomenclature. But one of them is the virtual, one of them is the real, and then L and AE are the same for both. Okay, now, what do we know? We know from physics that the external work has to be equal to the internal work. And if we're doing a virtual external and then virtual internal, then these two have to be equal to each other, which means then that 1 times the delta that I'm after is basically equal to the sum of FV times FL over AE for this guy. And so since this is a unit load, basically I can solve this guy for delta equal to some particular value. Okay, so it's a very simple formula as you start to kind of work on this. It's not too hard, and that's all there is to the method of virtual work, is that we're going to come up with a real system and a virtual system, and the rules for setting up the virtual system we've talked about, and that's all there is to it. All right, so let's give one a shot and see what we can do. You can come up with other types of virtual systems for axial loads. Maybe we have temperature effects, and you go through a similar definition that now, you know, if members change length due to temperature, I can do a temperature check and sum up all of the members. You know, and so, you know, delta T would be the change in temperature. Alpha is the coefficient of thermal expansion. We have our length, and we have an N, which is our virtual load. Okay, and that's going to be equal to 1 times delta. That's one way to write it. And then we can also do fabrication errors, that maybe the member was created just a little bit too long. Well, then the work that's done by that system then is 1 times delta, is the sum of all of the members, so the virtual load times the change in length, and we add up all of that for that energy. So it's all energy equations, and they all have this form of 1 times delta, because that's the unit load that's happening on this. Okay, and then the delta L in this equation will be the difference in the length between what was the intended size and what you actually put. Okay, all right? Okay, so here's what we have. So let's try an example, a basic problem. If we look at our structure, we have a simple truss, kind of like the one we saw in the last picture. I'm going to put a horizontal load at D of 35 kilonewtons. I'm going to put a vertical load at B acting downward in the amount of 84 kilonewtons. So you can see I can put loads anywhere that I want on the real system. Okay, we're going to define that EA is constant, so the cross-section in the material is the same for every member, that E is 200 gigapascals and A is 1200 millimeters squared. Okay, the dimensions are 4 meters from A to B, 3 meters from B to C, and then 4 meters from vertically from B to D, the height of the truss. Okay, so that means that this is, our 45-degree triangle, so 4 square root of 2 gets me that length, and this is a 3, 4, 5 triangle, so this guy's length is 5. Okay, so that's what we have for the real system. Okay, we want the deflection at B. Okay, and when we say that, that means we want both delta Bx and delta By. So we're going to solve these one at a time. Okay, now for our real system, if we went through and did our truss analysis with method of joints and method of sections, these are the values that you would see. Okay, my reactions are 35 and 56 to the right and up respectively, and then we have a 28 acting up at this support, and then what happens is I get a 35 kilonewton force compression here, I get a 79.2 compression here, 21 tension, and then 84 tension here. So these three are tension members, and those two diagonals are compressive members. Those would be your truss analysis from the real system. And the thing that's nice about this is we can use those calculations for all of our real systems that we're getting ready to set up. So what we do now is then we go in and we apply our virtual system. Okay, so the first one we're going to look at is applying a virtual system for the y direction. So our delta B in the y direction here. Okay, and so if we go through and we look at that, then we're going to have our basic system, which is going to consist of a 1 kip load at B acting vertically. Now, it doesn't matter the direction. You can go up or down. What will happen is it will change the signs, and then your final answer on the sign will tell you if what you assumed was right or wrong. So we're going to assume downward in this case, because that's kind of what we expect this structure to do. So this will be considered a 1 kilonewton load acting down. And when I do 1 kilonewton on this one, then I can solve for, using, again, method of sections, method of joints, all of the forces in this member due to this 1 kilonewton force. And you can see I got 0.71 compression, I have 0.61 compression, it looks like, 3.43 tension, 0.43 tension, 0.43 tension, and then 1 tension vertically there. Okay, so that would be the virtual system for a vertical load at B, for a vertical displacement at B. We go in and do the same thing for the horizontal at B, and so now my truss looks something like this. And so now I put a 1 kilonewton force at B acting horizontally because I'm after the horizontal delta Bx. Okay, and if I do the truss analysis on this, something interesting kind of shows up. All of these guys are 0, and the only one that has any tension in it is this one. Okay, so that's kind of interesting that the horizontal deflection is only controlled by this member's change in length. And so that will be one of the things that we look at. Okay, so those are our systems that we're going to look at. All that it takes to do this truss analysis then is we basically make a table. And we're going to make a table for every member in the system. And the table consists of the following columns. I have my member. So we've got AB, BC, AD, BD, CD. I've got the member's length. This is the L, so 4, 3. Here's 5.66. That's the 4 square root of 2 number. This is the 45-degree angle. Remember, a 4 and a 5. Okay, F is our real loads, and these were the forces that came out of our real truss when we analyze it. So we had 21 kilonewtons, and tension is considered positive, compression is negative. So we had 21 tension in the bottom chords. I have a minus 79.2, an 84, and a minus 35. These are just come out of the analysis, and I put those in this column. The next column then is specific to what we're looking for. So we're going to try to start out with looking for the delta By, the deflection in the vertical direction at B. And so I'm going to take the FV from that virtual system that we used to create this case. And so you can see I just simply took the truss numbers and rewrote them here. So minus 0.61, minus 0.71, 1 tension, 0.43, 0.43, and we have it. Okay, so then all I have to do in this is basically take all three of these numbers and multiply them together and then divide by AE of the member. So if I take 4 times 21 times 0.43, I get 36.12 divided by AE. Okay, and this becomes the work energy associated with that member. Likewise, I go and I look at 27.09 for the next one, 273, 336, 124. I just basically repeat this process for every member in it. So you can see it gets a little long, especially for big trusses. You have a lot of numbers happening, but they're all contributing. But something interesting shows up in here. You really quickly see which member is doing most of the work in the deflection. So for example, if you look at BD for the vertical direction, it's that member, that vertical member is the one that's contributing the most to the work energy. So if I wanted to make the deflection smaller, all I have to do is decrease this work energy calculation, and I can do that by making A or E bigger or different on that, and all of a sudden I can greatly change the deflections. Whereas if I change these two, it would only change it a little bit. It's these two guys that are the biggest. So it's kind of, you can see some interesting things come out of the work energy calculation. So if I take all that, I sum it up, this is 796.91 over AE. Okay, now I factored out the AE because it was constant for all of them. If your truss has different AEs, you would basically tally that number here, and then it would sum into just a single number down here. But because we said AE was constant, I just carried it through and factored it out. So it's down there. So then we apply our work energy calculation. It's 1 times delta By. It's going to be equal to that 796.91 AE number. And then all I do is basically plug in my values and I can solve for stuff. Now the units that come out on this are kilonewton squared meter divided by whatever the AE units are. Okay, so you got to kind of track those. And so because of the meters, I converted my cross-sectional area to meters squared. So it was given in millimeters squared. And so I'm going to multiply that by 10 to the minus 6. So that's this number. And then our 200 gigapascal number is now 200 times 10 to the 6 gets me 2 kilopascals on there. All right. And so if I do all of this math and I have my calculation figured out, then our final number is 0.00332 meters. Okay. And so that means that the deflection on this truss then would be 3.32 meters. Now, this guy was a positive value. What the positive indicates is if you go back and look at what you assumed on the virtual system, the positive indicates it's in the direction that you put the load. Okay, if I had gotten a negative number here, then it would mean it was going in the opposite direction. So positive meant that because I assumed downward positive on there, this guy is indeed acting downward, 3.32, because that number was positive. That's the hardest part of this whole thing, is getting the signs associated with it. Okay, all right, so then to do the horizontal in the X direction, I repeat the process. Again, you're just making this table. Everything here, the L and the F are all the same, so these values are the same. And the only thing that will change will be these two columns. And so that's what I've done, is I've replicated those two columns on for delta Bx. So my forces are AB had a 1 kilonewton tensile force and everything else was 0, which means then that my work energy calculation is 84 over AE and zeros everywhere else. So the work energy is 84 over AE. And then I plug into my energy calculation, 1 kilonewton times the delta is equal to 84 over AE. Do my units conversion like what we did up here, and you find out that the deflection is 0.00035 meters. Or in this case that it is, oh, I see a typo. This should be a 0.5. My pencil lead here. Should be a 0.35 millimeters, and it's positive. So we assume to the right on our picture here. It was to the right here. Okay, so because it's positive, that means that my deflection is indeed in that direction. And so that's 0.35 millimeters to the right. Okay. And so very, very easy to be able to set this thing up. So like I say, the final steps were we summed FV over FL over AE, the work energy, and then we basically calculate the 1 times delta of quantity. Okay, all right, and that's all there is to the virtual work for trusses. It's no harder than that. Now, again, there are some pitfalls on this. The biggest one is that you have to solve this truss twice. So if it's a really big truss system, it's not real convenient to do it, but it works pretty well, okay? And so it's possible. You just got to be very careful of the bookkeeping and the signs and things like that. But there is a real system for every member and a virtual system for every member. And the virtual system depends on the direction of the load. That's it. That's all there is to it. So I hope that's made some sense to you. Let's say virtual work for trusses is pretty easy, pretty straightforward. In the next video, we'll get into doing virtual work on other systems like beams and frames and stuff, and we'll proceed from there. So if you've got any questions or comments, leave us a note down below. I'll be happy to answer them. And then as always, if you found this useful, please be sure to like or subscribe to the video, and we will see you guys next time. Okay, happy engineering.